Welcome to Maths with EJD. I still continue with sequences and series, but I'm also branching out like I did under binomial series. So here our focus turns to Fourier series. I'll be doing Fourier series as a different playlist, but I'll also add it to the sequences and series playlist. So come along. In this video, our focus is on introduction to Fourier series. And basically, Fourier series is a mathematical tool, the mathematical tool used to represent periodic functions. I remember in the basic calculus playlist, I talked about types of functions. I'm sure I should have mentioned the idea of periodic functions. So Fourier series is a mathematical tool used to represent periodic functions as infinite sums, as infinite sums of sines and cosines. Okay. So Fourier series actually decomposes. It decomposes complex periodic signals. Complex periodic signals into simpler trigonometric components. So by doing that, enabling easier analysis, easier analysis and interpretation in various fields. I mean, we can already see here that the key idea here is the fact that Fourier series is a tool used to represent periodic functions. Periodic functions. So now the focus now is on periodic functions. What are those? Periodic functions. Okay. So a function, okay, yeah. So first we're starting out with the definition of periodic functions. So a function f of x, a function f of x is periodic if there exists a a positive constant t, which is called the period. So that constant t is called the period, all right, such that f of x plus t is equal to f of x. Okay, so if this is possible, then we can say that the function is periodic. That is f of x plus t is equal to f of x. And that happens for all values of x, for all x, for all x. So examples include sine, cosine, and many real world signals like sound waves, like sound waves. Of course, here the idea of periodic function is like we said, sine and cosine are examples of periodic functions. For instance, you know that sine zero is equal to sine zero is zero, right? So and sine 90 is one. Then when you go to sine 180, I think sine 180 is also zero. Yep. I believe sine 180 is also zero. Um and sine 360. Yeah, so 180 should be zero. I want to be very sure about that. So, okay, let me confirm. Here, let me use a Desmos. I think that helps. Yep. So Desmos. Yeah. Okay. So sine. Okay. Of course, we can do pi here, right? Okay. Let me use another operating system. Okay. Yeah. Yeah. This is better. So Desmos. Or in fact, we can just use Google, right? So zero, sine zero is zero, clear. Then sine 180 is also zero. And you see sine 360 is also sine 360. I think that should also be zero. Yeah, sine 360 is also zero. So in that case, you see then that sine zero is zero, sine 180 is 180 degrees, and 0 degrees, sine 360 degrees is zero. So it means at every 180 degrees interval, you actually get that value of zero, right? So, um, if I go to Desmos, right, sine 540 degrees, sine 540 degrees. Can I do degrees here? Oh, okay, that's not working. So, so that's like 3 pi, right? 3 pi. How do I get pi here? Okay, good. 3 pi. So you see, pi, sine pi is there is 180 degrees. Sine 2 pi is 180 degrees. Sine 3 pi is 180 degrees, and so on and so forth. So in that case, we can actually say that the period of sine is, so the period here is actually 180 degrees, because that simply means that when you have sine x is always the same thing as sine x plus 180 degrees. So here, t is 180 degrees. So the period for sine is 180 degrees. I think for cos, it's slightly different, especially if we look at the zero side of things. So for instance, you already know that cos, if we go for cos, so cos pi is minus 1. So what about cos 2 pi? That's 1. So definitely that's so pi is not the thing here. So you have cos pi. Then if you add another 180, that's 3 pi, right? So cos 3 pi is minus 1. So 4 pi won't give you that. 4 pi will give you 1. So you see that so automatically here it means 2 pi. If you have 2 pi, right, you get this value. Or you have 2 pi, that's 180. Then 3 pi gives you minus 1. 5 pi gives you another minus 1. 7 pi gives you minus 1. So you discover that from pi to 3 pi, that's actually 2 pi is the 2 pi is actually the period in that situation. So of course, this 180 degrees now, if in terms of radian, that's basically pi over 2. So pi over 2 is the period for sine. But for cos, right? For cos, you have, so for cos, if you have, if you talk about cos, so you see that cos pi in radians, right? That is actually cos pi is 180 degrees, yeah? 180 degrees. So you see that cos 180 degrees is the same thing as cos 360 degrees, and it is the same thing as cos 540 degrees. cos phi 40 degrees. So here you see that generally you have that cos x is the same thing as cos x plus 360 degrees. So here the period is 360 degrees, or what you can call 2 pi. So pi over 2, should it be 360 degrees? Now, 180 is pi, sorry, yeah. I was wondering. Yeah, 180 degrees is actually pi. Okay. 180 degrees is pi. Pi over 2 is 90, sorry. Then, so it means that the period for cosine is actually 2 pi, while is the period for cosine is 2 pi, while the period for sine is pi itself. Yeah, that's the idea here. So it means that after every of the period, come back to the same thing. For instance, if you start with sine 1, sine 1 is going to be the same thing as sine 181. It is going to be the same as sine 181 plus 180. So as you keep adding 180, you keep getting the same result like that. That's what this simply talks about. All right. So having done that, let's look at some properties of periodic functions. Properties, properties of periodic functions. So number one, we have repetition, as you can see already. There's repetition. So the function, the function repeats its values over intervals of length t. Okay. So after every period t, you get the same result again. Then you have symmetry also. That's if you plot that, you have symmetry. So periodic functions often exhibit symmetries such as even or odd properties. Next, you also talk about harmonics. Harmonics. So periodic signals can often be expressed as a combination of fundamental frequencies, and their harmonics. Okay, then that takes us to the idea of orthogonal functions. Orthogonal functions. So let's talk about the concept first of all. Concept of orthogonality. Orthogonality. So orthogonality refers to the property where the inner product, the inner product of two functions is zero, implying they are independent, implying they are independent. Okay, mathematically, two functions, f of x and g of x are orthogonal. They are orthogonal over an interval, over an interval AB. This is a closed interval for that matter. If the integral from A to B of f of x, g of x, dx is equal to 0. So if you integrate the product of two functions and you get 0, then you can say the functions are orthogonal. Okay? So let's talk about orthogonal basis functions. Orthogonal basis functions. So basically talking about sine and cosine. So in this case, in Fourier series, sine and cosine functions form an orthogonal, basis over a period. Okay. This orthogonality, this orthogonality allows any periodic function to be expressed uniquely as a as a sum of these basis functions. So that's the whole idea, right? You express periodic functions in terms of sine and cosine. Basically, that's the whole thing about Fourier series. Now let's do a bit of historical context. So what's the history behind Fourier series? Historical context. Okay, so let's talk about the name behind it is Joseph Fourier. Introduction to Joseph Fourier's work. So see that Joseph Fourier introduced, most likely was a Frenchman. Joseph Fourier introduced the concept of Fourier series in the early 19th century while studying heat conduction. While studying heat conduction. So he demonstrated that any periodic function, because we've seen that periodic functions are functions that they come back to the same value after a given period t. So he demonstrated that any periodic function, even with discontinuities, even with discontinuities, I talked about the idea of limits and continuities under basic calculus. You can check that out. Even with discontinuities, um, could be represented, could be represented as an infinite sum, as an infinite sum of sines and cosines, of sines and cosines. All right. So finally, let's talk about the importance of Fourier series in mathematics and physics. Importance of Fourier series. Fourier series is a fundamental. Fourier series is fundamental, rather. Fourier series is fundamental in analyzing periodic phenomena. So it finds applications. It finds applications in signal processing, acoustics, heat transfer, and quantum mechanics. Okay. Serving and quantum mechanics serving as a cornerstone, serving as a cornerstone for Fourier transforms. And modern harmonic analysis. All right, so that's the end of this introduction to Fourier series. So much of stories. I think that's what Fourier looks like. So we'll continue with the next video next time. You don't want to miss that, so subscribe to this channel, hit the notification bell, so you can always get alerted each time a new video is released. You also want to let me know how helpful these videos are to you, and if there's a topic or you'd like me to teach or a problem you like me to solve, let me know. And like and share so that more people can have access to these teachings. Bye.